Okay, so this is chapter 14. This all has to do with kinetics, which is probably a topic that is new for you unless you took AP chemistry before. We're going to start by talking about factors that affect reaction rates. So like speeding up reactions or slowing down reactions. So essentially, this is chapter, like I said, 14, and you can follow this link here to get to the online text if you need to, but that is not required for this course. So what is chemical kinetics? Essentially a study of reaction rates, which I kind of already mentioned. Study of reaction rates. You will see me abbreviate reaction as RxN often. Okay. This can also be used to shed light on how reactions happen, like their mechanism, because most reactions actually aren't like one step. There's usually multiple steps that have to occur. All right. So this is also sheds light on mechanisms. So we'll get to mechanisms later in the unit. All right, so it kind of can tell you what's going on. So I have an example here. It's called the iodine clock reaction video that kind of demonstrates kinetics. So I'm going to show that to you really quick.
Bearded Science Guy here, and today I'm going to show you how to make an iodine clock reaction. To start with, pour 128 milliliters of warm distilled water into a container. Then add and dissolve a crushed 500 milligram caplet of vitamin C. After that, stir in 12 milliliters of 10% povidone iodine. At this point, you're done with solution A, but keep in mind the better dissolved your reactants are, the more impressive the reaction will be. Start solution B with 40 milliliters of boiling water. Then add and dissolve 200 milligrams of cornstarch. The final ingredient for solution B is 100 milliliters of 3% hydrogen peroxide. Now that you have both solutions created, mix them together well and watch for the reaction. Triiodide reacts with starch to create a darkly colored compound. However, this reaction is only allowed to take place once another chemical reaction has run its course. You can even change the speed of the reaction by changing the concentration of the reactants.
So this is kind of where I want to focus. Notice he said you can change the speed of the reaction by changing the concentrations. So that one turned black really quickly because it had it had more concentration of your reactants than
this is simple kinetics, also known as the speed of chemical reactions. A couple of tips just in case your color.
So we could do this one in the lab. I could do this one as a demonstration if we had been in class, which is why I wanted to show it to you. So essentially, what is a reaction rate? It's going to be how fast a reaction occurs. Okay, so reaction rate is the rate at which and when your reaction's occurring, you would be using up your reactants and creating products. So we're really seeing how fast that can happen. So the rate at which reactants disappear or products appear. Now, these things are kind of hard to monitor unless they're like color changing or you create a precipitate or something along those lines. But we will be using a lot of color changing reactions to kind of monitor that progress in this unit. So like, what is the rate exactly? Like what kind of unit will we use? Well, we'll use change in molarity over change in time. Remember the triangle, it means change in. So the concentration is going to change over time, right? This is concentration. And this is, of course, time. So it's going to be molarity per second or molarity per minute or something like that. So the units, like I just said, are usually molarity per second. Chemical reactions happen quickly, not slowly. So you're going to see per second a lot of the time. Okay, and then I mentioned mechanisms a little earlier. So the mechanism is exactly how the reaction occurs. It explains the step. Exactly, sorry. How reaction occurs. Okay, it might have certain steps. Most reactions have actually more than one step in them. And they're based on molecule collisions. Different molecules have to collide. So molecule collisions. Okay, over here is an example of a mechanism. If you've taken biology or if you are planning to take biochemistry, you will absolutely see what's called the Krebs cycle. So I kind of zoomed in here so you can see you've got different molecules turning into other molecules via this little cycle right here. So for example, oxaloacetate turns into citrate in this reaction. Scrolling up a little bit, and then citrate into isocitrate and so on and so forth. And those are all the steps to get from one to the other. Okay, so to get from point A to point B. But of course, there's all kinds of reaction mechanisms in your body. So kinetics is extremely important in biochemistry, microbiology, things like that. All right, so I was talking about these molecule collisions. And so there's actually what's called collision theory, which explains the rate of those reactions, how it's based on collisions. So there are two things you need to consider when we're going to look at a successful collision. So one that actually occurs and produces a product. Okay, there are two things you have to have. One of those things is the correct orientation. Okay, so certain molecules might have to interact this way, certain molecules might have to interact this way. They have to be in a specific orientation in order to connect to the right atom, for example. They also have to have enough energy to react. Enough energy to react. This is known as the activation energy, or the EA. You will see it labeled for us, the amount of energy it needs to actually like activate for the reaction to happen. For example, if two molecules just brush past each other, they are not going to react, but if they have enough energy to actually collide and stick, we might get a reaction. So that's kind of what the activation energy represents. So what could increase the rate of the reaction? So what we want to do generally is to speed up a reaction so we can get more product faster. If you're thinking of any type in R&D or drugs or things like that we're trying to create, of course, we want to do it faster and make more. So how can we do that? Okay. Essentially, the goal then is to cause more successful collisions. Okay, and how do we do that? Well, we have to have more molecules that have the correct orientation and more molecules that have enough energy. So there are multiple ways to speed up a reaction. And I know it may be cheesy, but I love this video and it explains them and has analogies really well. So please watch.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, so it might have been a little bit cheesy, but it's a really good way to get all of those 5 ways to speed up a reaction to kind of like stick in your head. So we are going to put those in our notes now. So how can you increase the speed of a chemical reaction or essentially have more energetic collisions? First of all, concentration. More stuff, more collisions. Okay, so concentration would be increasing. Oh, I need my pen back. Would be increasing the the concentration, okay, which essentially is increasing. So I'm just going to use up arrows for increasing the number of particles which essentially leads to more collisions. Okay, so increased collisions. Okay, you can also do the surface area, or in our case, really changing the state. If you grind it up, if it's a solid, or if you dissolve it in water, if it is a solid, then you kind of make it more homogeneous, and then they've got more surface area, so you're going to have more of those collisions as well. Okay, so more surface area, essentially more contact or collisions, however you want to say that. More contact or collisions. Okay, temperature, as he had said, essentially means particles are moving faster. So you're going to have more particles that are at the correct energy or the activation energy. So moving faster increases energy. Okay, so they're going to have more energy or more particles that are the correct activation energy. And then a catalyst essentially will speed up a reaction by changing the mechanism. Changes mechanism, makes it easier. Essentially, it lowers the activation energy. So whatever the mechanism or the way they need to collide is easier for them to do. Please note, catalysts are never used up in a reaction. They can be used over and over and over, just like they had mentioned for a matchmaker.